welcome to this lecture module on optics. In the last lecture, we have seen a general introduction to the lecture module and optics in general, and I have briefly touched upon three different approaches which are used in studying optics. Today, we will right away start with the first topic, and the first topic here is reflection of light and formation of images, reflection of light and formation of images. The approach that we are going to follow is one of ray optics. As I mentioned, in the first part we will start with the ray optics approach. This will be followed by wave optics approach. Ray optics, where light is described, the propagation of light is described in terms of propagation of rays, and rays are straight line paths in a homogeneous medium. In this course, we will primarily discuss homogeneous media, propagation in homogeneous media, although one or two examples I may take up later of inhomogeneous media, but primarily we are focusing on homogeneous media, which means the ray paths are straight line paths. Therefore, they also follow the rules and formulae which we encounter in geometry, and therefore, this is also called geometrical optics. This part of the discussion also forms what is known as geometrical optics approach. So, first recall the laws of reflection. So, we know this is a plane mirror here. A ray of light incident on a plane mirror, or for that matter an interface between two media is reflected in such a way that the angle of reflection is equal to the angle of incidence. The angle of the dotted line here represents the normal to this surface. Say this point is a point P or point Q. The incident ray, the angle between the incident ray and the normal is called the angle of incidence, and the angle between the reflected ray and the normal is the angle of reflection, which we have denoted as theta r, theta I and theta r. So, the first point is that theta I is equal to theta r, that is angle of incidence is equal to angle of reflection. The second point is that now I have shown the same mirror in a little bit of 3D view here, and the angle of incidence, the point of incidence is P, and RP is the incident ray and PS is the reflected ray. The line here is a perpendicular line, and ABCD, what is shown here is a plane perpendicular to the surface of the mirror. It is a plane perpendicular to the surface of the mirror. So, the second law or the second point about reflection is that the incident ray, the reflected ray and the normal to the surface at the point P all lie in the same plane. RP, OP and PS lie in the plane ABCD. This is the plane perpendicular to the surface of the mirror. Now, an important point here is that if the ray was to reverse its path, that is, if the incident ray were to be like this, then the reflected ray would have travelled along this, because this would be theta I and this will become theta r, and anyhow theta I is equal to theta r. Therefore, a ray which is incident in the reverse direction will return in this way, or this is called the reversibility of ray paths, reversibility of rays. The same thing is true here as well. So, it is the same thing I have shown, it is in a plane, a cross section plane, and here a 3D view is provided. So, this is about plane mirror. Now, let us see reflection from spherical mirrors. We are interested more on spherical mirrors, because subsequently we will see that we will discuss some optical instruments and spherical mirrors and spherical optical components such as lenses are more widely used than the plane mirrors, and therefore, we are focusing more on spherical mirrors. So, reflection from a spherical mirror. In the last lecture, we have discussed about some of the optical components. So, what is shown here is a mirror. This is the top view of the mirror. So, the mirror's reflecting surface is here, is the top view. It is the spherical mirror is usually a circular section of a hollow glass sphere with a reflective coating on one surface. So, let me show here that when we show a spherical mirror like this, spherical mirror, then note that this is part of a hollow sphere. A hollow sphere, it is a circular section of the hollow sphere of certain radius of curvature. So, if this is the center, then this is the radius of curvature r. So, the spherical mirror is a circular section. This is of course, a cross section in the plane, is a circular section of a sphere of radius r, and usually one surface is coated with a reflective coating such as silver coated surfaces. So, that light incident on the light incident. So, this is the coated surface, and therefore, this surface is opaque. We have already discussed this. So, this is opaque and this is the reflecting surface. The front surface is a reflecting surface, reflecting surface. So, a ray of light which is incident here would get reflected, there is no transmission on the other side. Later on, when we will see about lenses, we will or refracting surfaces, we will see that a part of the beam will also be transmitted. But right now, we are looking at mirrors where we assume that all the light is reflected back. All right. So, reflection from a spherical mirror. So, this is the top view and this is the side view. So, as I said, it is a section of the sphere. So, you can see it is a hollow sphere, section of the hollow sphere. So, this is the part where reflection takes place from this region. So, this is the coated part, the back side of that section, and this is of course, a cross section in the xy plane. So, this is a concave mirror and a convex mirror. Concave mirror where the reflecting surface is on the front side, and convex mirror is where this is coated. From the inner side we have the reflective coating, and the bulged side, that is the convex side, is the reflecting surface. So, reflection from a spherical mirror. We will see first, this is the spherical mirror which is characterized by a radius of curvature, and we will see reflection from a spherical mirror. So, here what I have shown is incident of a ray, an arbitrary ray. Arbitrary ray means a ray which is incident at any angle, some arbitrary angle. In other words, if a ray is incident, this point M could be here, in which case if I start from some point, then the point M could be here or anywhere. So, that is why reflection of an arbitrary ray. How do we determine the reflected ray? First, at the point of incidence M, we draw a tangent. We draw a tangent to the spherical surface, and the normal to this here, the normal will form normal to the surface, and by law of reflection, the reflected ray, the angle of reflection theta r must be equal to angle of incidence theta I at that point. So, every point, every local point. So, if I have this as the surface, then every local point. So, a ray could be incident like this, or a ray could be incident like this, a ray could be incident like this. So, whatever way it is incident, so this point M is arbitrary, whatever way it is incident, then the rule is at this point you draw a tangent and then draw a normal, at that point of incident, and then we know that if this is the angle of incident, the reflected ray must go in a direction such that angle of reflection is equal to angle of incident. So, this is theta I and this angle here. So, let me mark it here is theta r, theta reflected. So, if you have a ray which is incident like this, again draw a tangent here to the surface, draw a normal to this, and then apply the law of reflection, namely angle of incident is equal to angle of reflection. So, this is for a concave mirror, where the back side here is coated, concave mirror. So, if you have a convex mirror, exactly like that. So, if we have a convex mirror, a ray of light is incident. So, you draw the tangent and then draw the normal to the tangent, and incidentally note that the normal to the tangent will pass through the center of curvature, because by definition any line joining the center to the circumference, that is a point on the circumference of the radius of the circle, will be normal to it at that point. So, here it will be 90 degrees, and therefore, the normal, for to locate the normal, there is no need of drawing a tangent and locating the normal. You simply link the center of curvature to the point of incident, and you have the normal to the surface. And then if the incident ray makes an angle theta I, the reflected ray will be in a direction where theta r is equal to theta I. So, reflection from a concave mirror and reflection from a convex mirror, reflection of any arbitrary ray. C is the center of curvature, P, that is the geometric center, is called the pole. So, we can have a look at this original diagram here. So, this is the geometric center. So, this is the pole, which you can see that it is the at the bottom here, P is in the same line, it is here P and it is here P, all of them are shown in the same line. So, P is called the pole. We will see the importance of this pole in the next slide. Reflection of rays incident at the pole. So, an incident ray at the pole, as before, this is the normal, because the line joining the center of curvature to any point on the circumference will be normal at that point, and therefore, this is the normal, angle of incidence is theta I, then the reflected ray will follow a path such that the angle of reflection is equal to theta r. Note that whether it is a concave mirror or a convex mirror, the ray of light incident at the pole will get reflected in this fashion. Theta I is equal to theta r. A special case is if theta I is equal to 0, which means if the incident ray is along the normal, then obviously the law of reflection says that theta r must also be equal to 0. In other words, the reflected ray will be along the same path, along the incident path, that is because this is the normal. So, whenever a ray of light is incident on the normal, then the reflected ray will also be along the normal. This is true for convex mirror as well, and therefore, the normal ray in both the cases of convex mirror and concave mirror will be such that the reflected ray will be along the normal. So, this the line joining the center of curvature. So, here is the center of curvature C, and the pole P is called the principal axis. So, this is called the principal axis. Principal axis. So, a ray which is incident along the principal axis will be reflected back along the principal axis in the reverse direction. Next, we consider reflection of a rays parallel to the principal axis. So, here reflection of rays parallel to the principal axis. So, what I have shown is, consider any ray, a ray which is incident here, which passes through a point F here, and another ray, parallel ray, also passes through the point F. In other words, what I have shown here is any ray which is incident parallel to the principal axis will pass through a point F, or if I look at this plane, the parallel ray, the parallel rays or the beam will be focused to a point F. So, this shows a converging beam. Please recall that a beam is a bunch of rays. So, we represented in the last lecture that beam is a bunch of rays. So, and a parallel beam or it is also called collimated beam, parallel beam of light, parallel beam, just to distinguish between a diverging beam and a parallel beam. So, in the last lecture we had seen that from the torch light you get a diverging beam. So, here is our torch light, then you have a diverging beam which is coming out, and we said that a beam can be represented by a bunch of rays. So, if parallel beam, which is, that is, parallel rays incident on the mirror, here we are talking of parallel rays parallel to the principal axis, because I could as well have parallel rays incident like this. So, this is parallel rays with oblique incidence to the principal axis. So, I am not talking about this right now, we will talk about this a bit later. So, parallel rays or rays parallel to the principal axis. So, what I have shown in this diagram here is that rays incident parallel to the principal axis all focus to a point F called the principal focus. How do we know this? We will see just in a minute. So, F is called the principal focus. In the case of a convex mirror, parallel rays, the same parallel rays incident will diverge, because every ray has to satisfy the law of reflection at the point of incidence, and the net effect is that they will lead to a diverging beam. As you can see, in this case a parallel incident beam was converging or focusing to a point here. Of course, after the focus it is again diverging, but we are looking at the focus. Focus is a point where an incident parallel beam parallel to the principal axis will get focused, that is called the principal focus. In the case of a convex mirror, the parallel beam results in a diverging beam after reflection. However, it can be seen that it appears that all the rays seem to start from, so this ray, for example, here this ray. So, all reflected rays appear to come from a common point, which is the principal focus of a convex mirror. The principal focus of a concave mirror is in front of the mirror, whereas the principal focus of a convex mirror is behind the reflecting surface, and we will discuss the implications of this in front and behind and the sign convention and so on. So, parallel rays incident on a plane mirror. Now, this principal focus, the definition where I had said that rays parallel to the principal axis focus to a point F. This is true under what is called as a paraxial approximation. Paraxial approximation. So, before proceeding further, I would like to discuss about the paraxial approximation. In this course, we will consider all the geometrical formulations under the paraxial approximation. This is a very good approximation in practice, I will discuss in a minute, but first what is paraxial approximation? Para-axial. So, this is actually the Greek word para meaning close by, nearby, para-axial. So, close to the axis or nearby the axis. So, we are looking at paraxial rays, which means rays which are close to the axis. So, let me draw here separately. So, here is the mirror, and most of the times I am showing concave mirror, but all discussions are equally valid for convex mirror. So, this is the principal axis. So, I have shown principal axis. So, rays which make let me use a different color. So, rays which make a small angle with this. So, this is the angle. So, this is a ray, incident ray. So, this is the angle theta. Small angles for theta small is a qualitative word, small. So, small means typically we are talking of anywhere from 0 to 5 degrees. Why 0 to 5 degrees? Because the main point which we will use out of this paraxial approximation is whenever we have tan theta or sin theta, this is nearly equal to theta. We will use this approximation sin theta nearly equal to theta for small theta, Of course, theta in radians here for small theta. This is a very good approximation for small values of theta. Tan theta is nearly equal to theta and sin theta is nearly equal to theta. This simplifies the mathematics, and that is why we often take course to paraxial approximation. So, paraxial approximation. So, paraxial approximation in which we deal with rays which are either, it could be parallel rays, when theta is 0 it is parallel rays. So, rays which are close to the principal axis, they could be parallel rays or rays which are making small angle with the axis, rays which make very small angle with the axis. So, then we say that we deal with paraxial approximation. This is also sometimes called small aperture approximation. Small aperture approximation. Let me explain what this means. Small aperture approximation. If we consider an optical system, so an optical system means a device which or a system or an arrangement with several optical components. Of course, to form some device, like for example, we will discuss later, we will discuss optical microscope, where we will see that there will be one lens here and another lens here, and they will be, I am not discussing any detail here, and they will have a certain separation between them. So, this is the axis of the optical system. So, there is one lens L1 and one lens L2. I just want to explain what is meant by this small aperture approximation. So, if you have an input aperture, there is a block here, aperture. So, if I have an aperture which restricts the extent over which light can enter this system. For example, light enters in this system. So, if I make a small aperture and light enters, and then maybe I do not know, it may be travelling whatever way, I do not know, I am just showing some rays. But if you see, if the aperture is very small, then only rays which are close to the principal axis can enter and can propagate further. A ray like this can also enter, but then it may go out of the system. A ray which enters at a deeper angle will go out of the system. Only rays which are close to the axis, which make small angles or very close to the axis, will pass to the next component and finally give whatever result at the output here. So, an optical system which has a small aperture primarily deals with paraxial rays. An optical system with a small aperture primarily deals with paraxial rays, and under paraxial approximation we will discuss the rest of the geometrical optics in this course. So, let me keep the diagram which I have drawn here and just paraxial approximation. So, I have shown some rays here. So, a ray which is making a small angle theta, a parallel ray, but very close to the axis. So, all of them, as you can see, the extent over which it is incident on the mirror is very close to the axis. So, a small aperture, which means if I put an aperture here, if I put a block here, let us say I put a block here. Block means an aperture and which blocks rays which are coming from other side. Then it will not affect these rays, because they are going back and forth, or I do not know, whatever. It depends on the optical system that we are discussing. For example, if I take, I showed the microscope in the earlier case. For example, there are optical resonators. In the last lecture I showed a laser. A laser has an optical resonator with two mirrors like this, and the rays go back and forth. The rays travel back and forth inside and resonate. So, they travel like this. Note that typically this length could be few of the order of 10 centimeters, let us say 10 centimeters. If I take a helium neon laser, this could be of the order of 10 centimeters, and the mirror here could be of the order of 1 to 2 centimeters, 1 to 2 centimeters, and this distance could be 10, 20 centimeters. Then we can see that any ray which makes a deeper angle, an angle which is larger with the optic axis of the system, will simply go off the system. It will not hit the mirror and come back. Therefore, only rays which are close to the axis, which make small angles, will go back and forth in this resonator. This is called an optical resonator, an optical resonator. I am just giving another example of an optical system. An optical resonator is a device comprising of two mirrors. It could be spherical mirror or plane mirror and so on, with a certain separation, and usually the separation and the dimensions are such that only rays which are close to the axis resonate inside this device, other rays simply go off, and therefore, we are automatically dealing with paraxial rays, and this paraxial approximation is very widely applicable in many components and devices in optics. So, it is in the first course, it is good enough for us to discuss paraxial approximation. So, small aperture approximation or paraxial approximation, the small aperture will lead to paraxial rays. So, paraxial rays close to the axis and oblique rays which subtend small angles. This is no hard boundary again, this is just I am saying, say a range of 0 to 5 degrees, maybe 6 degree, 5.5 degree, does not matter. Now, let me come back to the problem where I said that all parallel rays which are incident on this get focused to a point f. So, we said how do we know this? Let us discuss this. So, here I am discussing this topic, focal length of a spherical mirror. So, we have considered incidence of a parallel ray of light, a paraxial ray, a parallel ray at the point of incidence m. So, the reflected ray will follow a direction such that the angle of incidence, this is the center of curvature joined to the point m, gives us the normal. So, this is the angle of incidence theta I and angle of reflection theta I is equal to theta r, and in this geometry we can clearly see that if this is theta I which is equal to theta r, then this angle is also theta I, because this is parallel to this is the principal axis. So, incident ray is parallel to the principal axis. So, this is theta I, this is theta I, therefore, this angle is 2 theta I. So, immediately if I drop a perpendicular from m to the point d here, then tan theta I is equal to m d by c d, m d by c d, and tan 2 theta I is equal to m d by q d. For paraxial rays, the point m is close to p. We can see that we are discussing about paraxial rays, which means small aperture approximation. This point d is very close to this, because we can see this clearly, that if I have the principal axis here, when the ray is very close to this and perpendicular dropped from here, that is, this is point d and this is of course point p, the pole, and this is the incident ray and this is the principal axis, this is the mirror. Then any distance, if I consider this as the center of curvature c, c d or c p is nearly equal, that is c d is nearly equal to c p. And similarly, if I had a point as in the diagram q d, here there was a point q, then q d is nearly equal to q p. This is true if the point m is close to the axis or we are dealing with paraxial rays. Suppose I was to deal with a ray which is incident here, even a parallel ray which is incident far away, then if I drop a perpendicular here d, then c d would not be nearly equal to c p. And therefore, whenever we have a small aperture approximation, then the point m is close to the point p, this is close to the pole, and therefore, m d, the perpendicular which is dropped here is such that c d is nearly equal to c p. So, for paraxial rays, point m is close to p, c d nearly equal to c p is equal to r, r is the radius of curvature, because as I have already said, this is the center of curvature, the spherical mirror is part of a sphere and c p is that the distance is called the radius of curvature. Similarly, q d is nearly equal to q p. Further, we are dealing with paraxial rays and therefore, tan theta I is equal to theta I and tan 2 theta I is equal to 2 theta I. This gives us theta I is equal to m d by c d, which is c p, which is equal to r. So, theta I is equal to m d by r and 2 theta I is equal to m d by q p. This implies q p is equal. So, if you divide one by the other, you can see q p is equal to r by 2. Q p is equal to r by 2, r is the distance, c p radius of curvature, q p is equal to r by 2 for a parallel incident ray. Now, this q p, so what we have got is q p is equal to r by 2, radius of curvature is constant for a given mirror and therefore, this is a constant. What does this mean? We have taken a parallel ray where incident at a point m. The parallel ray could be here, the parallel ray could be incident here, the parallel ray could be incident here, which means the point m is arbitrary and the point m or mq or md, none of them appear in the expression. So, what it says is any parallel ray will pass through q, because the distance qp is fixed for a parallel incident ray. Whether the parallel incident ray is here or whether the parallel incident ray is here, that is whether this is m, it does not matter. It simply says it will pass through a point such that qp is equal to r by 2. It means any parallel ray will pass through q. The point q is called the principal focus and designated as f. Therefore, this point q, initially I had taken a general point q, but now we have showed that all parallel rays pass through the point q, and therefore, now I am calling it as f, which is the principal focus. And we can see here in the next diagram I have shown that all parallel rays pass through this point q. The distance f p is called the focal length, the distance from the point f, this q is the same as f. So, we have designated this point q now as f after showing that all parallel rays pass through it, which means a beam comprising of parallel rays will get focused to the point f, because it is a converging beam. So, it will get focused at the point f, and that is why it is called a principal focus and designated by f. The distance f p is called the focal length f, and therefore, what we have shown is we have shown q p as r by 2. So, q p is equal to f p is equal to f, or what we have shown is f is equal to r by 2. So, in this small derivation, what we have shown, there are 2 points which we have shown, that all parallel rays converge to a point which we call as f, which is called as f, the principal focus, and the focal length f p is shown to be equal to r by 2, where r is the radius of curvature of the spherical mirror, all under the paraxial approximation, or when we consider small aperture, this relation holds good. What about parallel rays incident inclined? What about parallel rays inclined to the principal axis? Parallel rays, but now they are not parallel to the principal axis, they are inclined at an angle. How would they look like? So, please see this. So, when parallel rays are incident on a plane mirror, they reflect and they are parallel. The beam remains parallel, because all the rays remain parallel to each other. Every ray satisfies the angle of incidence is equal to angle of reflection, but the beam remains parallel. Whereas, if there is a inclined ray, inclined parallel beam which is inclined to the principal axis, then they will get focused to a point, but that point q lies on a plane containing the focus. If we had parallel rays incident which are parallel to the principal axis, they would have focused to the point f, but if the parallel rays are inclined at an angle, then they will focus to a point q. This can be shown, they will focus to a point q, but it lies on a plane containing f, and that is called the focal plane, the focal plane. I have also shown the corresponding diagram for a convex mirror here. We are not going to the proof of this, but we see that when the parallel rays are inclined at an angle, then the focused point, the point where it is focused, or the point from where it appears to come after reflection, is shifted from the point f, but remains on a plane called the focal plane. With this background, we will now proceed to formation of image, formation of images. Formation of images. First, we consider image of a point object. If there is a point object, where will be its image? What is this point object? It could be a point source, it could be anything we see. For example, we see objects because objects reflect or scatter light which is incident on them. So, in darkness, for example, we cannot see any objects in perfect darkness. So, when we see object, it means object is scattering or reflecting rays which are incident on them, and they will form an image. So, where will the image of an object be? This is what we want to see, because as we know, the common application of all the mirrors is to see images, including the plane mirror which we use for the looking mirror, where we see our face, or when we use for dressing, or a concave mirror or a convex mirror, which are used in various applications, is to see the image of an object. Therefore, it is very important to know how the images are formed in a mirror, and what is the location of the image and what type of image is formed. So, that will be the next part of the discussion, and there we are. So, to begin with, we start with a plane mirror and a point object. So, here O is a point object. So, there is O, point object. So, if we want to discuss about image formation, let us say there is a mirror here. So, let me draw this here, and then I will put the figure which I have a pre-drawn figure. So, if this is a point object, then this will give out rays in all the, if it is a point source, it will give its own rays, but otherwise if it is just an object, then when it is illuminated by light, say the room light or any other light, then it will reflect or it will scatter light in all directions. So, this object may give out light in all directions. What we want to see is these rays which are incident on a mirror, where will they go after reflection and what kind of image, because this is coming from a point, and therefore, if the rays again converge to a point, that point will be called as the image point. So, this is what we want to discuss. First, we take a plane mirror, and then we will go over to spherical mirrors, and we look at a point which is sitting here and see, consider just one ray which is coming at an angle and a ray which is incident normally, and then we use the basic rules which we are aware of, that is, if this is a plane mirror, then the ray which is incident normally on the mirror will be reflected back, and the ray which is incident at an angle. So, this is the normal to the mirror. So, this is the angle of incidence theta I, then this will be reflected at an angle such that theta I is equal to theta r. So, this ray is travelling in the reverse direction, this ray is travelling in this direction, they do not seem to meet anywhere. However, if we take this ray backwards, then we will see that from this point. So, this is our object point, this is the image point, or from this point these two rays appear to come from this point I, and such point is called the image point. It appears to come, it is not, the rays are not coming from there, because there is no ray on the other side here, there is no ray here, rays are only in the front side, but they appear to come from, if we project them backwards, then they appear to come from a point I, and that is the image point. And that is what is shown in this diagram which I have drawn already, a pre-drawn diagram. So, we see the object O here, the incident ray normally will be reflected back, the ray which is incident at an angle will be reflected here. So, if we take this back, then it intersects at a point I. From the geometry here, we can clearly see that this angle, if this angle is theta I, that is incident angle is theta I, then this is theta I and this is theta I, and this is 90 degree, and therefore, all angles are the same and they have one common side here, and therefore, triangle OAB, this triangle and this triangle are congruent triangles, which means OB is equal to IB, this distance IB is equal to OB. What it means is the virtual image is a virtual image. A virtual image is an image point. So, this is a virtual image because rays are not physically traveling there. There are no rays existing in this direction. It only appears as if this ray and the ray which is returning back come from this point I. Therefore, this point I is called a virtual image point. So, I is the image point, it is a virtual image point, it is a virtual image point. Without loss of generality, we could have taken any ray at any angle. We have taken a point A here, but the point A could as well be here. This could have been A, this could have been A, any of these could have been A, and every time we will see that if this were A, we see that this triangle will be these two triangles will be congruent, it tells OB is equal to this. If this were the ray, then these two triangles will be congruent, and again it gives OB is equal to IB. In other words, every ray which is coming out of the object is such that all the rays, all the reflected rays appear to come from this point I, which is the image point. The point A is arbitrary, which means it could have been any of the point, it could have been anywhere here, and therefore, I is a virtual image point. This is how we can locate the image of a point object in front of a plane mirror. Why are we first interested in a point object? Because any extended object can be represented as number of point objects, that is points on the object, on the extended objects. Each point on the extended object can be treated as an independent object, and its location can be found out by applying the laws of geometrical laws of reflection and subsequently of course, refraction, and we can locate the image corresponding to that point. And when all the points, all the image points, when we get all the image points, we get the total image of the extended object. That is why we start with a point object. Now, if I see the point object of a spherical mirror, due to the point object in front of a spherical mirror and try to locate its image point, then let us see the image of a point object in the case of a spherical mirror. So, here is the spherical mirror, here is the point object O, and we consider two rays, one ray which is travelling along the principal axis, and we have already seen that it will be reflected back along the same direction, a ray which is propagating in this direction, an arbitrary direction it is, that is this point Q could have been here as well, in which case I have to join O to Q. So, that will be the ray path OQ. So, OQ is the ray path, incident ray path on the mirror. It will follow the law of reflection and get reflected, because C is the center of curvature, the line joining C and Q is the normal to the surface, and the angle of incidence the small angle here and the angle of reflection must be equal. So, that leads to the reflected ray which is propagating along this line. It intersects the second reflected ray at the point I. So, the point of intersection must be the image point. So, by taking the earlier example here, what we have shown is we considered two rays and the point of intersection. In this case, it is a virtual image point, that is they appear to come from this point. The point of intersection is the image point. So, in this case the image point is the point of intersection of two real rays, that is the ray actually travels here and gets reflected. This ray, the ray along the principal axis propagates here and gets reflected and comes back along this line, and at the point I this ray would go further. At the point I, the two reflected rays would intersect, which is the image point. This is a real image, because real rays, it is the intersection of real rays, whereas in the earlier case it was an intersection of two virtual rays, that is there are no rays on the other side of the mirror, but they appear to come from that point which was the image point. So, the point q is arbitrary and therefore, the object distance and image distance will satisfy a relation independent of q. We will show this, that the object distance O to P, this point is P, the pole, OP is called the object distance, IP is called the image distance. We will discuss this in detail. We will show shortly that the object distance and image distance has a certain relation which is independent of the point q. So, the point q is arbitrary, the object distance and image distance will satisfy a relation which is independent of q, and therefore, the image point will be this, these considering any two ray will be sufficient. All other rays will come to the same point I, because this object, this point that we have chosen is arbitrary. All other ray means what? A ray could have been here, which means the point q I would be choosing here. So, that is what I meant by all other rays. A ray could as well be incident here, then the point q would be here. So, this point q is arbitrary and we will get a relation which does not depend on q, and therefore, it is sufficient for us to pick any two rays and get the image. Similarly, if I look at the image formation in a with a convex mirror, then here is the first ray travelling along the principal axis which gets reflected here. The second ray, I have chosen a second ray to be incident here, which gets reflected following the law of reflection here, and both these rays appear, this ray and this ray appear to come from a common point I, which is the image point, and in this case again I is a virtual image. Now, we discussed the image due to a point object, but in practice we look at extended objects. In practice, objects are extended objects, point objects is a 0 dimensional object, but a laterally extended object, for example, if I take an arrow like this. So, this is an 1D object, one dimensional object, a line object basically. We have shown an arrow, but it is basically a line. So, it is a 1D object. If I take an object like this, so this is a 2D object. So, 2D object. If I consider a 3D object, for example, let me try to draw a cube. So, the object could be a 3D object. So, a 3-dimensional object. Of course, what I have drawn are regular objects, but there could be an arbitrary object, an object of arbitrary shape, which is a 3D object, but of arbitrary shape. We first discuss some of the regular objects and image formation due to regular objects. The first step would be to discuss image formation due to a 1D object, that is, we have discussed a point object. Now, let us look at a line object, which means it comprises of many points here. So, every point, rays are emitted or rays come out from every point on this here. So, if we can locate the corresponding image point for every point here, then we would be able to locate the object, the image of the object after reflection. So, we will discuss formation of this extended formation of these images in the next lecture. Thank you.